Okay, now that we've solved this initial value problem, and we got that y is equal to cosine 2t minus sine 2t, can we rewrite this solution as one cosine or one sine so that it's easier to plot and then we know certain properties about it like amplitude, phase, and period? So this actually is not really going to be a lesson in differential equations, but actually kind of a reminder lesson in trigonometry. So we're going to start with our solution, C1 cosine omega t, C2 sine omega t, and we're going to see if we can turn that solution into a single cosine. So these are the steps that we're going to take. First, we want to find out what the amplitude is, and to figure out what the amplitude is, why not figure out where the maximum of this solution curve is? Because the maximum, of course, is the same thing as the amplitude of our oscillation. So we're going to differentiate to find the maximum. Okay, so the derivative here is going to be negative omega c1 sine of omega t plus omega c2 cosine of omega t. And then we're going to set that equal to 0. Okay, so that tells us, first we can divide out the omegas. Okay, and then we can write this as sine of omega t times C1 is equal to C2 times cosine of omega t. In other words, we can say that the tangent of omega t is equal to C2 over C1. So the maximum occurs when WT, so that maximum time, omega t, is equal to the arctangent of C2 over C1. So now if we plug that maximum into our solution, we should be able to find out the amplitude, that maximum value. What is y of my maximum time? Well, that's going to be C1 cosine of arctangent of C2 over C1 plus C2 sine of arctangent of C2 over C1. Now, some of you may have memorized formulas for cosine of arctangent. I can never remember these things. So what I do is I like to draw a right triangle. And so here I'm going to have my omega t max. That's my angle. And then I know that tangent of omega t max is actually equal to C2 over C1. So it's going to be equal to C2, the opposite side, over C1, the adjacent side. That means that the hypotenuse is the square root of C1 squared plus C2 squared. Okay, so the cosine is going to be the near side, C1, right? That adjacent side over the hypotenuse. So that's C1 squared plus C2 squared. And then the sine is going to be the opposite side, C2, over the square root of C1 squared plus C2 squared. So what we essentially have here is C1 squared plus C2 squared over the square root of C1 squared plus C2 squared. That is the square root of C1 squared plus C2 squared. So the amplitude here, okay, is the square root of the sum of the squares of the two coefficients. Okay. Now let's look at what the phase might be for this oscillation. What is phi going to be? Okay. So I'm going to suggest here that phi is equal to the arctangent of C1 over C2. Okay, so I think that that's the phase, and then I'm going to show you that that's the phase that works out. Okay, so if that's the case, okay, what is, if phi is going to be the arctangent of C1 over C2, then I'm going to draw a right triangle with a phi 1, or with a phi, okay, and actually, let me fix that. It's actually going to be C2 over C1. Okay. And so, again, I have this kind of same right triangle where the opposite side is C2 and the adjacent side is C1. And then I have the square root of C1 squared plus C2 squared on the hypotenuse. Okay, so we again have that cosine of phi in this case is going to be the adjacent side C1 over the hypotenuse, square root of C1 squared plus C2 squared, and then the sine of phi is going to be C2 over the square root of C1 squared plus C2 squared. Now, so I'm starting with this guess about what my phase phi is going to be, and then I'm going to show you that it works. Essentially, I'm going to plug phi in right here to my equation and show that that works. Okay, so the way that I'm going to do this is I'm going to take this left-hand side here, okay, and I'm going to expand it using a famous trig identity, okay? The fact that the cosine of A minus B is equal to cosine A cosine B plus sine A sine B. So I'm going to expand that. So I'm going to get, in this case, cosine of omega t, cosine of phi, plus sine of omega t, sine of phi. Okay. Now, in this case, let's take the cosine of omega t and then multiply it by what the cosine of phi was. I'm kind of going back up for a second. Cosine of phi was C1 over the square root of C1 squared plus C2 squared. And then I've got the sine of omega t, and then the sine of phi was C2 over the square root of C1 squared plus C2 squared. And so you should see here that this amplitude cancels with those two denominators. And so this is equal to C1 cosine of omega t plus C2 sine of omega t. So in other words, we chose phi correctly so that if we use that trig identity, then we can rewrite, okay, our linear combinations of cosines and sines as just a single cosine. Okay, so now we can say that the oscillation can be written as A times cosine omega t minus phi, okay, where the period is given by 2 pi over omega. Okay, the frequency there is omega. Okay, the amplitude is the square root of C1 squared plus C2 squared. And then the phase, phi, is actually the arctangent of C2 over C1. And if you write your oscillation as just a single cosine, then it's easier to plot. So I want to go back and make sure that we understand how to use this information. So here we had y of t. Our amplitude in this case, because C1 and C2 are 1 and negative 1, so it's the square root of 1 squared plus negative 1 squared. So that's the square root of 2. And then phi in this case is going to be the arctangent of negative 1, and that's a negative pi over 4. So I can actually rewrite this as the square root of 2 times the cosine of 2t, because that's omega t, minus a negative pi over 4, or plus pi over 4. And that's another way to write that oscillation. Okay, so that tells me that the period, okay, for this oscillation is going to be 2 pi over 2, or pi. Okay, and there's going to be a shift to the left by pi over 4. Okay, let's see that. Let's look at in Desmos. Okay, and so here I've plotted cosine of 2x minus sine of 2x. Okay, it seems that square root of 2 is a good measure for the amplitude. Okay, it does repeat every pi, and it is shifted over to the left by pi over 4. So I'm actually going to superimpose the single cosine on top of it that we got, and notice that I get the same curve.